attempt, though of great help to us, was not all that we expected. So the experiment was put forward until much better records were made. Special devices, lights, and shutters were developed for this study. Also special oil that represented consistency of 20 oil at 280 degrees in a room temperature of 70 degrees. This eliminated the fog due to vapors from the oil. The new for oil at 0 temperature and accelerating the car to top speed. It shows clearly the pressure stream that is intercepted by the connecting rod dipper for about 3 inches. The speed of the engine is about 3,900 or about 80 miles per hour, car speed. At this speed, the oil enters the dipper at the rate of 120 miles per hour.
It looks to me as if the system is delivering a lot more oil to the cylinder walls in the present job.
Within the engine at high speed. The problem required that we study these results quietly and leisurely. Our first as rapidly as possible, holding this maximum speed until the oil temperature rises to normal for operation. This oiling system and bearing permits this abuse without failure.
Amazing instruments is one that enables engineers to see a sound happening. This device, called a stroboscope, has the curious effect of slowing down a moving object or making it seem to stop. The stroboscopic. So they cushioned the contact with a film of oil. On the other end of the rocker arm, they could see another noise. Then the engineers reshaped the surfaces to give a sliding contact. And developed a
has been tamed, made to do man's bidding. Scientists have harnessed this titanic force of the thunderbolt, used it as a powerful battering ram to break into the hidden worlds of the molecule and the atom and the electron. In the High Voltage Research Laboratory at Barberton, Ohio, this giant lightning machine builds up a charge of over 2 million volts. A flood of energy that staggers the imagination is held in banks of storage condensers until it is ready for use. And the man
device splits light into separate narrow rays so that the path of a beam can easily be followed. Notice that a light spreads out from its source in all directions. We can see how a mirror reflects light, how a prism bends the rays in different directions, and how light can even be bent around corners in tubes and pipes. Now let's see the effect of a simple reflecting surface used to control light. The rays leave their source, strike the reflector, and bounce back on themselves in the same path. Then if we place a lens like this in the path of the light, the rays are bent inward. Now let's try another type of lens, similar to the lens used in automobile headlights. Instead of bringing the rays together at a point, this lens bends them so they go out in parallel lines.
With the photography, they are able to study the motion of the air around a moving object. A stream of air will be blown against this block. We will be able to see what happens to the air just as if the block...
We can see that the fan blades, which are attached directly to the revolving discs, are whirling a constant stream of cooling air over the heated surfaces, drawing the heat away from the running parts and sending it away into the air as rapidly as it is produced. With its careful design and its accurately blended friction materials, the clutch can transmit the power of the engine to course, the clutch is larger and more efficient. The friction disc is covered with special materials so that the surfaces will be soft enough to make a gradual contact, yet firm enough for plenty of friction and long life. The design of the clutch plates prevents noise and vibration and carries away excessive heat caused by the friction. Until very recently, 9 spiral coil springs were used to squeeze the plates together. Engineers knew that the more a coil spring is compressed, the greater the resistance it offers. The pressure increases rapidly as the spring is squeezed together. This meant that the spring is checked on the Magnaflux machine to make sure that it does not contain any minute flaws or cracks. Not a trace of a crack in this spring. Before it goes into the car, every spring passes a test that shows its springiness to make sure that it will give the right amount of soft pedal control.
We see what happens over the 72-hour period in just a few seconds on the screen. The rubber sample immediately begins to swell. Soon it reaches the bottom of the jar. Now it has swollen so much that it has no place to go and curls around the bottom. Such a severe test may
be measured in millionths of an inch, 8 millionths under the pressure of a few ounces. How small is 8 millionths of an inch? Compared with the average thickness of a human hair, magnified thousands and thousands of times under the microscope, 8 millionths of an inch would correspond to the thin white line in the center of the hair. That's how far the finger bends the rail. Farther and farther beyond the range of the human eye, we can lose ourselves in a newspaper reproduction of a photograph until nothing is left but meaningless dots. How sharp
shows the path of the ride lights as the car travels over the bumps. The wavy lines show the excessive pitching. Now begin.
It can show us at what speed the ball is traveling at any given point. Here we can only see proof of this experiment come to life. The spaces between the images of the ball show how it slows down until at one point it comes to a complete stop. And then as it falls toward the ground, it again picks up speed until it reaches the girl's hands, where it decelerates to a stop all at once. This unique method of photography can visualize the answers to any number of startling questions. For example, automobile. Judging by the relative size of the spaces between the wheel images, this looks like a perfect stop. And a special graph placed over the picture offers mathematical proof of the rate of smoothness at which the car decelerated or lost speed as it came to the stop.